last lecture by Zamponi.
Okay, so I brought to the blackboard a recap of what we did last time. So let's go through it quickly. So we are studying this spherical P-spin model, spherical P-spin glass. I tried to motivate it as a toy model for more complex problems where you have disorder and these rough energy landscapes. And okay, the definition of the model, I remind you, it's a linear combination of p-spin interactions with different p and some coefficients alpha p. You can decide at which point you truncate in p, but I mean, it's not very important. The important point is that these j are Gaussian variables, independent, with these variance and zero mean. And so the whole thing is constructed in such a way that the covariance of the Hamiltonian of two different configurations is a function of the scalar product of the two configurations. And this function f of q is an arbitrary polynomial of q. Okay, so if you tune the coefficients, you can do more or less what you want. Now, we focused on the generic situation that you get when p is bigger than 2. We said p equal 2 is a special case. For any p bigger than 2, in the generic case, you get this situation. You have also more exotic cases, but okay, I can give you references. And so what's the situation that we discussed? Well, there are two transitions. There is a thermodynamic phase transition at the temperature Tk, and there is a dynamical phase transition at a higher temperature, TMCT. This is the glass physics notation. So this is called Kautzmann temperature, and this is called mode coupling temperature because they emerged. I mean, the Kautzmann temperature was introduced by Kautzmann, and the mode coupling was appeared in the mode coupling theory. In other communities, this is sometimes called the dynamical transition. This is called the condensation transition. So it's a matter of notations. But okay, what happens is that at high temperature, you just get a paramagnetic system. So all the local magnetizations are equal to 0. Maybe I should write it. The local magnetizations are just the average of spin I. Okay. So you have one state. When you lower the temperature, you have this dynamical transition at which the dynamics becomes arrested. So if you initialize the system in equilibrium in a configuration and you run the dynamics, the trajectory cannot go much far away from the initial condition. And this is because you have an exponential number of these metastable states that trap the dynamics. And then at the lower temperature, this entropy of the states goes to 0. You have a finite number of states, and that's where you have the thermodynamic glass. So the way to see that, I introduced this order parameter. So we have two order parameters, one for the dynamics and one for the thermodynamics. So the one for the dynamics is maybe a bit more intuitive. So you compute the scalar product. So you remember that we are working on a sphere. I forgot to say that the spin sigma is a spherical spin. It is constrained to have a scalar product equal to 1, okay? So you initialize your dynamics in a certain state that you draw from the Boltzmann distribution. Then you run the dynamics, and you look at the scalar product between the initial state and the state at time t. Okay? So at time equals 0, this is 1 because of the spherical constraint. When time increases, this goes below 1. But then you take the thermodynamic limit, you take the long time limit, and you look if this goes to 0, which means that the trajectory can go on the orthogonal space, and it's essentially the most you can do. So it's the total decorrelation if you want. So if this is 0, you are in a you can decorrelate in the paramagnetic state. If this is non-zero, then it means that you remain stuck in this things that I called either cones, if you want to think in terms of this sphere, or metastable states, or just states. So this is the dynamical order parameter, and so the average here is an average over the dynamics in equilibrium. So I draw the initial state from the Boltzmann distribution, and then I run Langevin dynamics at the same temperature, and I take the average over the noise. And I can take the average over the disorder. I told you that in the thermodynamic limit, this average is actually not needed in the sense that this thing has zero fluctuations in the thermodynamic limit. And so if I look to the dynamical overlap, what I get is 0 in the paramagnetic phase, so I get the correlation. When I lower the temperature, the correlation function decays slower and slower, so the relaxation time that is plotted here becomes bigger and bigger until at the dynamical transition I get an infinite plateau at a finite value of Q, okay? So the relaxation time becomes infinite and I can never escape from this cone in the thermodynamic limit. The static order parameter that I also introduced, but in a bit, in a quite sloppy way. So the more precise definition is this one. So you take two replicas, two copies of the system, okay, one and another one, and the joint probability of the two replicas is the product of the Gibbs distribution for each of them. So you take two independent configurations from the Gibbs distribution, but you put a small coupling. So you favor, you see this term will favor aligned configurations. So it's like, you know, when you do a ferromagnetic system, if you want to select one state, you have to put a small magnetic field in the direction of the state, take the thermodynamic limit first, and send the field to 0 next. So here you do the same. The only problem is that you don't know where are the states, because there is disorder. So you cannot put a field, because you don't know where to align the field. So what you have to do is to let the system do it by itself. So you draw first a configuration. If there are these states, the first configuration is going to be trapped in one of the states. And now if you want, you are using here the first configuration as a field that acts on the second one. So the second one is given as the same Boltzmann distribution, but maybe I should specify that here the couplings should be the same. Of course, it's the same system. So the second configuration feels a kind of magnetic field that is aligned to the first one. And then you are going to take the thermodynamic limit. You are going to send the field to 0. If the two configurations, when you send the field to 0, become uncorrelated, it means that there are no states, or that there are too many states. I will discuss that in a second. If you can keep a correlation, then it means that there are states that are thermodynamically stable, okay? And so this static order parameter, what happens? So, okay, here it's 0, fine, because there is only one state, the paramagnetic state, where things are decorrelated. But when you cross the dynamical transition, it actually stays 0. And it stays 0 because there are exponentially many states. So even if you try to bias the second system to be in the same state as the first one, the entropic drive, the number of states is so big that it's still convenient for the second system to go in another state. So that's why the system here looks paramagnetic. It's dynamically stuck, but there are so many states where it can be stuck that in a probabilistic, in a thermodynamic calculation, you don't see it. When you reach the Kautzmann point, the number of states is no more exponential, it becomes finite. This I didn't show, but you can show it. And so then a little bias can align the two copies, okay? So to compute this thing, well, you have to do what is called the replica calculation, and then you have to do the famous replica symmetry breaking, and you get this. Okay, so there is this region here. So here you have a spin glass, here you have a paramagnetic state, and here you have this hybrid thing that it's not clear what it is, but it's a situation where you have all these very many states that block the dynamics. And if you look to the relaxation time, I told you that it diverges at the mode coupling point. In a finite system, what happens is that the relaxation time is always finite, because at finite n you always equilibrate, but below TMCT it will grow exponentially with the system size. Now, yes?
Are both the K and TMCT exponents in the denormalization group?
Sorry?
Are both the step, thermodynamic phase transition and the dynamical phase transition fixed points under the denormalization?
Yeah, this is a very interesting problem that is open somehow. What I presented here, this is a mean field picture, okay? So then you can say, okay, if I take a system with space and I try to run RG, what happens? Well, it's not clear. I mean, so the Kautzmann transition is a static phase transition, so you can try to do some standard RG. I mean, you have to do RG with disorder, so it's functional RG. I mean, it's technically a bit complicated, but you can do it. And the problem is that the Kautzmann transition is somehow it's a first order transition from the point of view of the order parameter, even if the energy is continuous. And so you have to do it, so it looks like if you do RG for a first order. So you don't have an upper critical dimension. But you can find, within some approximations, you can find fixed points where you have a Kautzmann. The MCT is much more complicated because the MCT transition is like a spinodal point. Is a point where these states become unstable. Now, a spinodal point, as soon as you go to finite dimensions, is unstable. But you can still try to do perturbative RG. And for example, in the case of ferromagnet, if you do perturbative RG around the spinodal, I think you get an upper critical dimension of 6, which means that down to 6, it looks similar to, if you neglect the fact that it's metastable, so it will decay non-perturbatively and so on and so forth. If you neglect the non-perturbative things, it looks like mean field. So in the case of this kind of models, it has been done, and there is an upper critical dimension of 8. So above 8, it stays kind of mean field. Below 8, you have. But then the problem is that when you go below 8, it's hard to make sense of the perturbative series, because then there are non-perturbative things that make the thing decay. So, I mean, it's a big problem. I can give you, if you send me an email, I can give you some introductory references to that.
Just a short question. In quantum cases, do we expect the fact that spin can tunnel from one cone to another prevent the dynamical transition, or doesn't it?
It doesn't. So there is this, if you look to there is work by Letizia Cugliandro and co-workers. So you can do a phase diagram in temperature and, for example, transverse field. And what you get, you have TD here and you have TK here. So what happens is that there is a line of first order transitions here. So this is a true first order transition, and then you get something like this. So you have paramagnetic, spin glass, and this strange dynamical phase that remains there for finite, I mean, in a region of transverse fields. And here, it's a first order transition where you have an exponentially small gap. So if you try to do quantum annealing, it fails because here the gap is exponentially small. Sorry, can you speak a bit?
Yeah. How does Whittaker century breaking come into this picture? Because I assume that, you just mentioned that if you do the calculation, you would find.
Yes, so replica symmetry breaking is precisely related to disorder parameter, because, I mean, okay, this is a bit technical. I mean, to compute yes, so the point is that when you, in order to calculate disorder parameter, you have to take this average over the disorder, and you have two replicas. But the problem is that in the partition in the probability, the disorder appears in here, and it also appears here. So now what you have to do is to use an identity where you write 1 over z as the limit for n going to 0 of z to the n minus 1, okay? So you get n minus 1 replicas here. So now you have 2 replicas plus n minus 1 plus Sn minus 1. So you have 2n replicas. And you have this symmetry without this term. This term breaks the symmetry and divides the replicas in 2 blocks. And so the question is whether the symmetry remains broken when epsilon goes to 0 or not. So this is something that, I mean, there is a really beautiful paper by Blandin that if you are curious about a bit of also the history, it's a paper of 1978. I think I can give you the exact reference where he discusses this. But the problem was how to break the symmetry, and then, okay, then there is the work of Parisi who understood how to break the symmetry. If you want to see a simple case of this, you can do the random energy model, and I mean, on my webpage there are notes where you can do the calculation for the random energy model, and you can see how why the symmetry is broken. But I cannot really enter into that. Okay, so the plan for today is to discuss the out of equilibrium dynamics for the p-spin in the first hour, of which I already spent some, but okay. And if there is time in the second hour, I wanted to introduce very quickly, I mean, just in a simple way, the second toy model, the perceptron, that is interesting for the connection to machine learning kind of problems. So let's look now at the out of equilibrium dynamics. So what do we expect? Well, I mean, what we expect, I would say above TMCT, what we expect is that if we prepare the system at high temperature and we bring it to a lower temperature above TMCT, in a finite time it should go to equilibrium. Below TMCT, it shouldn't go to equilibrium. So what happens? So what I'm going to discuss is the simplest protocol, because then things depend on the protocol. So the idea is, okay, we have this phase diagram. This is the one there, okay. We are going to prepare the system at very high temperature. Well, not very, I mean, okay, this is TK. This is TMCT. We are going to prepare the system in equilibrium at some temperature, initial temperature T. So, and then we are going to bring instantaneously the system to 0 temperature. And then we let the system relax. And we expect that the system will go down in energy. And the question is, where does it stop, right? Do we reach the ground state? Here is the ground state energy, or not. So, okay, so we start here with the Boltzmann distribution. This is our initial state. And then we run the Langevin dynamics at 0 temperature. Now, the Langevin dynamics at 0 temperature is the gradient descent dynamics. And we wrote it yesterday. It has this form. And then there is the noise, but the noise is 0 because there is no temperature. And we should fix this mu. And, well, now it's easy to fix. Mu, you remember, is the term that we need to remove the longitudinal part of the gradient in order to keep this condition. So in order to keep this condition, we want the derivative of sum over I of sigma I squared to be 0, because we want to keep this to be a constant. So this is equal to 2. Well, it's proportional with we want this to be 0, so let's forget the 2. So this is going to be this is the scalar product of sigma with the derivative of sigma. There is a sum over I. Well, let's write it in vectorial notation, it's easier. So it's sigma scalar product with the derivative of sigma, and so this is sigma, and the derivative of sigma is minus the gradient of h minus mu sigma. And this should be 0, so we get mu, okay, let's say this is minus sigma gradient of h minus mu sigma square, but sigma square is equal to n, so minus mu n. And this should be 0, so what I get is that mu is equal to minus 1 over n sigma times the gradient of h. Okay? Yes, is this, sorry. Gradient with respect to sigma, yes. H, I'm always thinking to h as a function of sigma because sigma are the variables that I want to minimize. The j and the alpha are parameters that I specify at the beginning and they are fixed. So, okay, this is my dynamics. You can easily run it on a computer. Yes, because I'm bringing the system to 0 temperature. Okay, I prepare the system in equilibrium at a given temperature, but then I bring it to 0 and I want to know what happens. You can also do the same thing at finite temperature, so you can do a quench from initial temperature to final temperature, but it's just a bit more complicated, so, and it doesn't change much. There was another question, okay. Okay, so this is the dynamics, and okay, what happens? Well, before I tell you what happens, there is one thing that I want to show, which is the following. Okay, we are doing gradient descent, so it should stop when the gradient is 0, right? So if well, the problem is that the gradient also has this term. So what I expect is that sigma of t will converge to some sigma infinity, which is a solution of the equation minus gradient of h minus mu sigma equal to 0. Okay, this is my, but I don't know the solution, of course. What I know is that when in the final stages of the gradient descent, when I approach sigma, I should be able to linearize the dynamics near the final state. So I define delta sigma as sigma minus sigma infinity, and I linearize the equation above. So what I get is that the derivative of delta sigma with respect to t is equal to what? Well, I have to linearize this, so maybe I should write it in component. Derivative of sigma I, if I linearize the thing there, I get sum over j of minus the second derivative of h with respect to sigma I, sigma j, minus mu delta ij times delta sigma j, right? So what I get is the Hessian matrix. I'm just doing harmonic approximation because I'm saying, okay, I'm going down to some local minimum. Let's do harmonic. Let's do a study of the harmonic properties of this minimum.
Since mu is also a function of sigma, should we have some correction characterizing because mu
yes.
is sigma itself, or is it only by order correction?
It's a higher order correction because, well, it's also, I think it's a 1 over n correction if you work it out because mu is an average. So yeah, this is the mu infinity, is the value of mu in the final state, right? Okay, so let's compute the second derivative of h. Now, so because we want to know, of course now we want to know the eigenvalues of this matrix to understand how the thing will relax to the bottom of the minimum. Now, if I call this matrix Mij, so, okay, let me save some space by, I will call Mij this matrix, maybe with the plus sign, just to, let me just check, but I think yes, yes. So the eigenvalues of M control the, I mean, the equation for sigma is delta sigma equal to minus M delta, the derivative of, so the eigenvalues of this matrix will control the exponential decay of delta sigma. So I have this matrix. Let's write this down. Well, maybe let's not write this down just to save some time. But you see that if I fix, if I take a pure model with only one P, so I set all the alpha P to 0 except 1, then this is a, I mean, this thing is a sum of products of P spins. When I take a derivative, I drop 1. When I take the second derivative, I drop another 1. So this thing is something like a sum of J I1 IP times sigma I1 sigma I P minus 2. I mean, I have 2 less spins. Okay, you have to write the indices. The point is, now I want to compute this in the final state. The final state depends on the J. So this thing depends on the J and depends also on the dynamics. So it depends on everything. So this is a random matrix, but it's a complicated random matrix because in principle these things are Gaussian, I know, but these things are complicated things that I should get by solving the gradient descent. They will depend on the J, they will depend on the dynamics, and so on and so forth. Except that you can show, and I don't have time to do that, that in the thermodynamic limit, you can forget the correlation between the J and the sigma. So you can treat the J and the sigma as if they were uncorrelated objects. So the corrections that come from the correlations are subleading in N. So in the thermodynamic limit, if you consider that these sigma are given, because you want to compute your matrix in sigma, infinity, then this is a Gaussian matrix, because it's a linear combination of Gaussians, right? So again, if it is a Gaussian matrix, the only thing you need to know is the average and the variance of a matrix element. So you can compute it. So the average of M, the average of this is 0, because this is a linear combination of J's, and the J's have 0 average. So the average of Mij is just mu delta Ij, mu infinity. Well, mu infinity is the one computed in the minimum, right? And the variance is, sorry, it's not the, I mean, really the variance, you have to subtract the mean square. The variance is given by, so you can do it as an exercise, it's given by f second of 1 divided by n, where f second is the function, this function, okay? So this is now a simple object, because it's a diagonal matrix plus a matrix that has matrix elements that have 0 mean and certain variance. Of course, it's a symmetric matrix. So this is a GOE. It's a GOE matrix, right? M is, and so the spectrum of M. If I look to the spectrum of the eigenvalues of M, this is given by the semicircle law. So it's going to be the square root of lambda minus mu square minus 4 times the variance divided by pi square root of f second of 1. This is my spectrum, and it looks like this. It's a semicircle, and the two edges are given by the values where this thing is 0, so it's mu plus minus 2 square root of f second of 1. Okay? So the dependence of this on the final point is only in mu. We should remember that mu has to be evaluated. Mu is given, I erased it, but okay, let's keep it here. Mu was minus 1 over n sigma times the gradient of h. And this is a function of sigma that has to be computed in the final state. But apart from that, all the rest, this is a constant, okay? It's a property of the model, but it's the value. You take this thing, you take two derivatives, compute it in q equal 1, and it's a constant. So this means that the spectrum is centered in mu, and depending on the value of mu, the spectrum will shift to the left or to the right. Now, of course, if we want this to be a local minimum, we want the spectrum to be positive. We want all the eigenvalues of the stability matrix to be positive. So this means that lambda minus should be positive. Okay. Now, let's take the pure p-spin. So what we call the pure p-spin, again, is that all the alpha p, so f of q, all the alpha p are 0 except 1. So f of q is equal to q to the p divided by 2. So by the way, f second of 1, the term that appears here, is given by p times p minus 1 over 2. So this is the constant here. Now, if I compute this thing, mu, what do I get? Well, you can work it out. I mean, when you take the gradient, you remove a sigma, but then you put it back. So what you get is that mu is given by minus p times the Hamiltonian divided by n. Okay, so this is true for the pure p-spin. So this is interesting because this means that the mu, which is the parameter that controls the spectrum, is actually proportional to the energy. So if you make a drawing of the energy, what happens? So mu is minus the energy, okay? So let's call E the energy per particle, just to have something that this is finite in the thermodynamic limit. So when energy is very small, mu goes up, and the spectrum goes to the left, to the right, which is fine, because we expect that the more we go down and the more we have minima. When energy goes up, mu goes down, and the spectrum becomes unstable. And there is a point which corresponds to the value when mu is equal to 2 square root of f second, right? And this value, we're going to call it threshold value. This is the value when lambda minus is equal to 0. So the spectrum is precisely touching 0. well. So the energy that corresponds to that is called the threshold energy, and it is given by minus P minus 2P square root of P times P minus 1 over 2. I think I made a mistake somewhere. I don't recognize the energy, but sorry, yes, because energy is sorry, it's this divided by P. So this is minus whatever, it's minus square root of P minus 1 divided by P 2, well, it's some value. Anyway, this is the threshold. And what I've just shown is that all the stationary points of the energy, that have energy above this threshold have a spectrum that is unstable. So here, the stationary points have some negative directions. This is a multidimensional thing, so there are many positive directions, but also many negative. So you should imagine. When I reach the threshold, states are flat. They have some zero mode. And when I am below the threshold, I get minima. Okay? Yes, sorry, this is a cartoon. It's a cartoon of the energy function in the multidimensional space, or on this multidimensional sphere. Okay. So what I did here was to say, okay, let's take a stationary point of the energy. Let's compute the spectrum of the small vibrations around the stationary point. If you accept this statement that I made, that is non-trivial, that you can neglect the correlations between the J and the sigma, but this is mathematically proven to be true in the thermodynamic limit for this model, then the spectrum is a GOE, and the important point is that the center of the spectrum is, for the pure P spin, is a function of the energy. So this means that I have a sharp transition between a region of energy where all the stationary points have some negative direction, and the region of energy where all the stationary points are stable. Okay? Did I lose all of you, or is it? Okay. So now if you have this picture in mind, where do you think, if I do what I was saying, so I prepare my system, let's do it. I was telling you that I prepare my system at a certain temperature, T. I quench instantaneously my system to 0. Let's use a different color. I prepare the system here, I quench it to 0, I let it relax. Where would you expect it to stop? Well, if you look at this, a good candidate for a place to stop is here, okay? Because you're doing gradient descent. So if the system starts above the threshold, it will follow the gradient, so it will go down the negative directions until it reaches the point where there are no more negative directions, and that's where you stop, okay? And this is exactly what happens. So you have to solve the dynamics. So when you solve the dynamics, I mean, you have to do what I said yesterday, this dynamical mean field theory, where you obtain closed equations for the correlation functions, you solve them, and what you find is that indeed, if you start above MCT, if the initial temperature is above TMCT, then the limit for long times of the energy of the gradient descent dynamics is given by the threshold. So this was a very important result that was obtained by Cugliandolo and Kurchan in a PRL of 1993. Okay? So if you instead start below MCT, what happens? Now, this is not so interesting because I told you that you cannot start in equilibrium below MCT. At least if you have a normal computer and you're trying to equilibrate by cooling, you will never be able to equilibrate below TMCT. So this is maybe a bit academic, but let's check it. What happens? Well, what happens if you start below MCT is that you are actually starting in one of these metastable states that are essentially finite temperature version of this minima. So you are in the basin of attraction of one of these minima. You are at finite temperature, so you are vibrating around this minimum. When you do gradient descent, you are just going to reach the bottom. And since these are stable minima, because if you are below the threshold, the spectrum has a gap, so then relaxation is exponential. So you get that in this case, the energy of gradient descent is going to be some final energy that is called the energy, in the glass literature is called the energy of the inherent structure. It's the whatever, I mean, it's some energy plus essentially exponential of lambda minus t. So lambda minus is the edge of the spectrum. It will control the relaxation to the minimum. It's because it's harmonic here. And this is a temperature that is below the threshold and depends on the temperature of the initial state. Because when you change temperature, and if you're able to go below TMCT, you go to deeper and deeper states. So when you do gradient descent, you just relax to the bottom of these states. You look a bit lost. So do you want to ask some questions, or I keep going? I don't know. Okay, let me say one last thing, and then we can take a break, and maybe you can ask me more questions. Yes?
In the first case where the initial temperature is greater than TMCT, what is the final temperature of the state?
No, I'm starting in equilibrium at the initial temperature, and then I'm running gradient descent. So I'm taking my system, I thermalize at the initial temperature, then I switch off the thermal bath, and I just let it relax at 0 temperature.
So the final state is the non-equilibrium.
Yes. Yes, because in principle, so sorry, that's my point. Sorry, I forgot to say that the threshold energy that you can compute is given by this value is bigger than the ground state energy. So you are not going, in principle, at 0 temperature, you would go, I mean, if you are in equilibrium, you should go to the ground state. And you are not going to the ground state because the ground state is here. But above it, there are all these minima that are the 0 temperature version of the exponential number of metastable states that I described before that block your dynamics. And so your dynamics stops at a much higher.
And at the point where if you started at T less than TMCT, then you would be able to.
Yes, because the point is, if I start below MCT, if I assume that I can equilibrate below MCT, it means that I'm able to jump the barriers, because below TMCT I have these stable states, this exponential number of stable states, so I have to jump, and so this takes an exponential time, but if I'm able to do that, then I will reach the basin of attraction of one of the minima, and when I switch the temperature to 0, I just go to the bottom, okay?
Right? You don't do any below, you don't go below that, right? And
I stop at the first stationary point that is stable.
But is this like this related to this like rough energy landscape that like settle down on the first?
Yes, sorry, this is a different cartoon of the same thing. So I mean, this thing, It's a bit hard to, but these things will be connected by, so this is the rough thing that, I mean, what I'm saying is that you have these basins. This can be a little bit misleading because actually we don't know if the barriers that connect two of these go through the threshold or go above or below. This is an open problem, but anyway. So this is the rough landscape, and above it there are these subtle states.
You don't go to the even more stationary points because you're stuck at those stable ones that already are like at this threshold.
Yes, exactly. The last thing I want to say is, how do you get to this threshold? Maybe I'm out of time, I don't know. Oh no, I started at 20, no? So I can have 2 minutes.
Yeah, take your time.
Yeah, no, but I don't want to. I mean, there is lunch. Yeah, but then there is lunch at some point, so I don't want to. So how does the energy relax to the threshold? And, well, we don't know. I mean, you have to solve numerically these DMFT equations, but there is an argument, there is a simple argument that is maybe not exact, but it gives you an idea. And it goes as follows. So I know that the energy is asymptotically going to this threshold energy. So let me call delta E of T the difference, E minus the threshold. And this is proportional to delta mu of T, actually minus delta mu of T, because the energy is proportional to mu. This is true, this is exact, this is true at all times. So where mu threshold is this and delta mu is mu minus mu threshold. So the energy is minus the mu, so delta energy is minus delta mu. Now, imagine that your dynamics is going down these saddles, and at some point you are at some level of energy. This is my delta E. And you have, and you are there. What do you see? Well, what you see is an unstable spectrum where this is delta mu. Okay? Because when mu is equal to the threshold, the spectrum is here, and the spectrum is shifting in a rigid way with mu, so this is delta mu. So this means that you have a fraction of negative directions that is the integral of rho. So the number of negative directions, actually the fraction of negative directions, so is I have n eigenvalues. The number of negative eigenvalues divided by n is the integral between minus delta mu and 0 d lambda of rho of lambda. Okay? Now rho of lambda has a square root singularity here, so I can write it as square root of lambda plus delta mu, I think. So I can compute this integral, and this goes like delta mu to the 3/2. Okay? So the number of negative directions goes like and this delta mu is also delta energy. Maybe there are, well, because delta energy is positive, delta mu is negative, so there are absolute values everywhere, but okay, don't. So the important point is that delta mu is also delta E. So this gives you this picture. You are the point that is doing the gradient descent. You go down in this high-dimensional landscape. You arrive at some point, delta E, above the threshold. You look around you, and in most directions, you go up. There are a few directions where you go down, and these are the ones you want to take. Now, suppose this is a very hand-waving argument, suppose that you take a direction at random. So suppose that these directions are kind of rotating randomly in space when you move. So you take at random a direction. The probability that you go down is delta E to the 3/2. So if you go up, it's not good, so you don't go. If you go down, then you're happy. So how much time it takes to go down? Well, 1 over the probability. So the time it takes to find, if the gradient is moving around this saddle, the time it takes to the gradient to find the negative direction is related to energy in this way, according to this very rough argument. So if you invert this gives you delta E going like T to the minus 2/3. So you go down and you approach the threshold in a power law way. This is above TMCT, of course. Below, I told you it's exponential. So here, energy is going like the threshold plus a correction that goes like T to the minus 2/3. So we don't know if this argument is correct, but what we know is that if we solve the equations numerically, we see a power law, and the exponent is very close to 2/3 for the pure p-spin. Within error bars, looks like 2/3, but okay. We don't have a proof that it's 2/3. But okay, so this gives you a consistent picture of what's going on. You have this very complex landscape with all these minima, but on top of all the minima, above it, there are all these saddles, and the number of negative directions that you have in a saddle is going to 0 when you approach the threshold. So when you go down, you move, you get stuck because there are very few negative directions. You take one, it brings you to a saddle that is slightly lower in energy, and now you are stuck again, so you have to look around, you have to find a new one, and so on and so forth, and so you go slowly to the threshold. While below, when you are near to the minima, you go exponentially because there is a gap in the spectrum and you just go. What did I want to, there was one last thing I wanted to say before we stop, but I forgot it.
What happens with this energy? It dissipates in the environment, or where's it go?
No, this is, yes, you can think like that. I mean, but it's zero temperature dynamics. So you should imagine that you have a system that is being, well, it's coupled to a zero temperature bath that is sucking all the energy. You are just doing relaxation dynamics, pure relaxational dynamics. So yes, I mean, it's not a microcanonical dynamics, it's a gradient descent. So it's, yeah, there is a thermal bath, but it's a zero temperature thermal bath. That is just getting out energy.
Can I also ask?
Sure.
I hear some people talk about like this glass dynamic stuff.
This what, sorry?
Glass dynamic systems, which they say like, oh, we don't even know it was when you have this glass transition, you can even like from dynamic equilibrium and stuff. Could you comment like what they mean? I mean, that's like.
Yes, yes. So. Yes, so let me say the thing I wanted to say that I forgot because it's connected to this. What I wanted to say that I forgot is that this is also if you, I told you this at zero temperature, so you equilibrate at high temperature and you go to 0, but actually if you do the same and you quench to a finite temperature below MCT, you get the same. You get power law decay to some value of energy that is slightly above the threshold. So in general, in the mean field picture, you have this idea that above TMCT you can equilibrate, and when you quench below, you have this slow decay of the energy, and the system is out of equilibrium forever. Now, the debate on the glasses is due to the fact that in the real glasses in 3D, this is mean field. In 3D, you can always, I mean, in mean field, the time it takes to jump from one state to the next is exponentially in n, so it's very slow. In finite dimension, it's not like that. It's the time it takes is typically, you can think it's finite, because it's like when when you have if you have a ferromagnetic system and you start in the metastable state, you can nucleate a bubble of the stable state, and it will take a finite time to jump. So the idea is that in that glass, You don't get stuck to the threshold because you can start nucleating the states that are below, but then there is no precise theory of that. So the question is, can you reach equilibrium or not? But what is clear is that the time it takes to nucleate is slower and slower when you go down, so you never reach a TK. So that's maybe related to the question that I got on the first day, what's my opinion on the existence of a thermodynamic transition in glasses. So what you can do, now I introduced it, so you can do this Q, you can try to measure the Q, the thermodynamic Q. I told you that the Q thermodynamic is the limit of epsilon going to 0, limit n to infinity of Q1, 2 of two coupled replicas. So you can try to do this calculation numerically in models of glass, but the answer is not conclusive because when you approach this region of temperatures, you always go out of equilibrium. So doing equilibrium measurements, it's essentially impossible. The point is that maybe this is also useful to say, in a normal phase transition, the relaxation time diverges as a power law in the distance to the transition. But in this case, the relaxation time diverges as a power law of a temperature that is above the transition in mean field. And in the finite dimensional case, all the theories that we have agree that it's not a power law at Tk. If there is a Tk, it's still exponential of 1 over T minus Tk. So it diverges much, much, much faster than in a normal second order phase transition, which means that you cannot go very close to Tk anyway. So you fall out of equilibrium before, and now the problem is that in a normal phase transition, like in a ferromagnetic case, you know how to prepare the equilibrium states below Tc. Here we don't know because we don't know the minima below Tk. So from above we are stuck because the dynamics is low. From below we cannot go because we don't know how to, and so essentially we don't know, and I don't think, I mean, some people even think that it's not that important to know because, you know, maybe there is a thermodynamic transition, but you're not going to see it, so it's better to try to understand what happens to the out of equilibrium system that is the one that you see in nature. That's the... Anyway, okay, maybe let's stop here so we can restart maybe at 12:30. Is it okay? 10 minutes is okay. Okay, so let's try. I want to try to give you an idea of the perceptron because I think it's an interesting model. So, okay, for the p-spin, we more or less got a complete picture, at least for the pure one. So the main result is that we have this threshold. Below the threshold, there are all these states that block the dynamics and makes it exponentially hard in n to reach the ground state. I said, okay, for the pure p-spin, everything is clear. When you study mixed p-spin, so when you have more than one p that contributes, it's more complicated, but okay, more or less it remains similar, but a bit more complicated, and if you're interested, I can give you references. Now, let's move to the second toy model, just to... So, it's called the perceptron. It was introduced in the 50s as a model of a neuron. People wanted to model neurons, but then it has been understood that it's basically the simplest, it's the first building block of a deep neural network. So it's the most stupid network you can imagine. You have an input. So imagine I give you an input, and so we are now in the setting of the classification problem. So I give you an input, x, and I give you a label. So x is my image. The label is cat or dog. So I give you the input, and you want to predict the label y. So, well, today we do these big networks. The perceptron is just a single layer like this. So you try to fit the problem by saying that y, I'm going to use binary, well, Okay, I'm going to use binary labels, -1 + 1 instead of 0, 1, but it's the same. So you say, okay, y, it's going to be the sign of some vector sigma applied to the input. So you take your input, you project it onto these vectors sigma, and this gives you, you take the sign and you get the output. So if you want, I say this is the first block of a deep neural network because it has this structure where you do a linear transformation on your input and then you apply a nonlinear function. Here is the sign. In general, you can replace the sign by hyperbolic tangent or something else, and then you can stack many of these and you get your deep thing. Okay, so let's see. Now my vector sigma is still on a sphere. I can put it on a sphere because, as you can see, the sign, I mean, if I scale sigma by a constant, the sign doesn't change. So I can normalize sigma on the sphere. And what do I want to do? So let's say that I have many images with their labels, and I want to learn sigma in such a way that I want to classify them. So what I have to solve is something like ym is equal to sign of sigma dot xm for m equal to 1 from 1 to m. So x and y is my training set, sigma are my variables, and I want to solve this problem. Well, I can multiply everything by y. So if y is equal to the sign, this is the same as saying if that y is that 1 is equal to, sorry. I mean, this thing should have the same sign as y. So this means that the product of y times, y is a number. These are vectors. So this product should be positive. This is the same as the other one. And now I can call psi m equal to y times x. And so what I want is that sigma dot psi m should be positive. Okay?
Sorry, maybe I lost it.
Yes.
Both sigma and x are binary variables.
No. Y is a binary label, plus minus 1, and sigma is a continuous, is as before, as in the p-spin, these are real numbers, and x I didn't specify. I'm going to do it now, but for the moment x is some vector in n dimension. Can be binary, can be continuous, whatever. Okay. So what's the geometry of this thing? So this is my vector of weights. Usually it's called W, but I call it sigma because I want to use the same notation of the p-spin, okay? But okay, in machine learning, usually the weights are called W or something like that. Anyway, I give you an input with its label. This is an n-dimensional vector. You multiply by the label that is plus minus 1, you get psi. So this will be some vector, psi. For example, for the first training point. Maybe it's not on the sphere, but it doesn't matter because you see, I can always rescale because this condition is only that it's positive. So I don't care about the norm of the vectors. So let's say that the psi are normalized in the same way, okay? Psi square is equal to n, like sigma. So I have these two vectors on the sphere. The constraint is that the scalar product should be positive, so it should be on the same side. Well, okay, sorry. This is not a good. So, sorry. This is psi, 1. I take the orthogonal plane, and sigma should be on the same side of the orthogonal. So my first training point cuts the sphere in two, and half of it is good, the other half is not good. Now I take a second one, and maybe it's like, I don't know, like this. So it will cut another half space, and so on and so forth. Now, before I discuss this a bit better, let's generalize a little bit this thing. So let's put here a constant kappa times square root of n. So the square root of n is there just for normalization, because these vectors have norm n. If they are random, the scalar product is of order square root of n. So in this way, this constant is of order 1 in the thermodynamic limit, but this is a constant. So of course, if this constant is equal to 0, I recover this problem. You can show, and I will give you the link to an exercise and the solution, that if you take kappa to be positive, what you are asking is that you can classify the data in a way that is robust to noise. So if you solve this problem, if you solve this for all m, now your weights are such that this is true. But on top of that, if you add a little bit of noise to x, the amount of noise that you can add depends on the value of kappa, of course, this is still true, okay? So if you ask that kappa is positive, then it's even more robust classification. So now we want to solve this problem, okay? So let's do it again. How does it look like? This is the first obstacle. This is the first training point. I want sigma to have a scalar product bigger than something. So this means that now my obstacle is fixing a certain cone, okay? And this is the good region. Now I draw a second obstacle. Well, if it's like this, then it's over. I cannot solve the problem. If it is like this, and I have a second region, then I still have a region here that is the intersection of these two, right? Okay, this is the, sorry. Anyway, you see, I mean, so whenever you add the new training point, you have to intersect this cone with the other ones, and so you have this region that becomes smaller and smaller. Yes?
I'm not sure I understand
how psi relates to a training point. So a training point is a vector, x, that is something, an image, for example, together with a label y that tells you cat or dog. And psi is just the product of each component of x times y.
So which value is the values in y?
Y is plus minus 1. I take plus minus 1 for convenience because I use the sign here. Otherwise, if you change the sign into something else, you have to use, let's fix 1. I mean, if I take the sign, then y has to be.
And if you impose that constraint on psi, then what is that constraint?
No, the constraint is on sigma, sorry.
The one below over there, that it has to be.
This doesn't matter. I can. What I mean is, I'm just normalizing my input to have some value just to be able to compare things. So if kappa is equal to 0, which is the problem without any noise robustness, you see that the norm of these vectors doesn't matter because I'm taking a sign. So I can rescale the vectors as I want. And so I first rescale them, and then I I add this additional constraint to make it robust to noise.
So you rescale them just because you want to draw them on the same scale.
Yes, that's it. Okay. Okay, so now you see two things. The first thing is that for kappa positive, the problem is convex. The solution space is convex in the sense that, okay, when you have one obstacle, it's a spherical cap. When you have two, it's an intersection of two spherical caps, which is still convex and so on. So it's always convex. And the other thing that you see is that when you add obstacles, sorry, I keep calling it obstacles because when you add points in your training set, the more points you have, the more difficult it is to find the solution, of course. So let's now focus on one specific problem, which is the problem of fitting noise, okay? Why would you like to fit noise? Well, so first of all, let me tell what I mean by fitting noise. I'm going to take the vectors x. I'm going to take xm to be a Gaussian vector. So the probability, so each training point is a Gaussian, IID Gaussian with zero mean and unit variance, okay? So I take random inputs, just random inputs, and on top of that I take random labels. Okay, there is nothing to learn here. But still, what I can do, I can ask how many inputs and how many of such random inputs can I correctly classify. And this gives me an idea of the what is called capacity of the machine. Which is how many data points I can classify. And this is a measure of somehow of how expressive your machine is, okay? If you can classify more points in the training set, then maybe your machine is more powerful. It is also related to some bounds on learning, but okay, that's a bit more, I can give you a reference, I mean, as a motivation. Okay, of course, the reason I do that is that this is easy and you can solve it. But also, so this is the first, let's say, A. Also, after you do this, you can generalize it to a slightly more interesting setting, which is called teacher-student, in which you still generate the X at random, so you take random inputs, but now the Y are not random, they are decided by a teacher. So there is a teacher T, it's a vector on the same sphere. You decide the labels by applying the same thing with the teacher. So now you have random inputs, but non-random labels. And the question that you can ask is whether, when you fit, you can learn the teacher. So the student is going to be the sigma, and the question is, for example, do I have enough, how many points I need for sigma to be aligned to T, so that the student has learned the teacher?
In this case, the student could not be the teacher.
What?
The student could never be the teacher in this case, or...
Why can never be?
No, I'm asking if it could the student...
If you have enough points, yes. So that's the point. There is a phase transition when you increase the size of the... So the important parameter, sorry, let me introduce it. The important parameter in this game is the ratio of how many points you have in the training set to how many dimensions you have in space. So if alpha is big enough, there is a phase transition at which the student polarizes in the direction of the teacher. And in the case A, when we increase alpha, so what happens? So this was my point. So what I can do now, I draw here alpha, and I ask the following question. So I fix n, I fix the number of dimensions of my input. I fix m, the number of training points. The training points are totally random. I draw them, so now I have all my vectors on the sphere. I do this intersection. Is the intersection empty or not? If it is empty, it means that there is no solution to my problem. So I call it unsat. Okay, there is no solution. So empty. Let's call V the volume of the space of solutions, so the intersection of all these spherical caps. So if the volume is 0, then there is no solution and the problem is unsat. If there is a finite volume, so then it means that I can take sigma here, and this is my solution. So what I can do is I can draw here the probability of being sat. This is a probability over the training set. Okay, I fix the size of the problem, I fix the size of the training set, I draw the training set, xy, from this law, I compute the space here, the volume. If it's positive, I say, okay, 1. I put a 1. I do it many times. I do the average of this 1. This is my probability. How does it look like? Well, okay, at alpha equal to 0, the training set is empty, so this is 1. At alpha equal infinity, it's going to be 0. And, well, of course, if you add new vectors, the probability of getting a solution should decrease, so it will be something like that. And let's say that this is for n equal 10. Now you do it again for n equal 100, and you get something like this. You do it again for n equal 1000, and you understand where I'm going to end. So this is increasing n. So when n goes to infinity, there is a sharp phase transition at which this probability drops from 1 to 0. So there is an alpha, a critical value of alpha that has many different names, so I'm going to check the name. How did we call it in the notes? Well, anyway, let's call it alpha C. Let's call it alpha C. That separates a SAT region to an unsat region. In the thermodynamic limit, okay? So this is a generic phenomenon. It happens in the perceptron. In the special case where kappa is equal to 0, you can compute exactly this probability at any n and m. This is done, it's a paper by Cover from the 60s. It's cited in the, well, I can give you references, I will not give. So you can compute it and you can trace this curve and you can show that it's like that. For kappa positive, the calculation of this volume has to be done using replicas, because what you want to do, this volume is like a partition function. It's the partition function of sigma in presence of the xi. The xi are random, so the xi are a quenched disorder like the couplings of the p-spin. So you have to compute the partition function of sigma for given xi, and then you have to take the log and you have to average. So you can do it with replicas, and it's famous paper by Elizabeth Gardner in 1987. That is a really milestone, I think, in the field, where she did this calculation and found the same transition. So this point depends on the stability parameter, and well, and you have this sharp phase transition. So this is a generic thing that happens in any random constraint satisfaction problem. Because here you see that you have to satisfy constraints. Each training point gives you a constraint, and you have to satisfy all these constraints, and the constraints are random, and so you have this phase transition. So for example, it is the same kind of thing that I showed in the first lecture when you have spheres and you want to pack spheres in a volume. Each pair of spheres has a constraint that they shouldn't overlap. And the more spheres you add, the more constraints you have. And at some point, you cannot satisfy them, and the spheres have to overlap. So you get this transition from floppy to rigid. So in the context of the computer science literature on satisfiability, this is called SAT-unsat transition. In the context of particle systems, it's called the jamming transition that goes from unjammed to jammed. And in the context of machine learning, it's called the capacity transition. So here you have perfect classification. So below alpha C, your machine is able to perfectly classify all the data, while when you cross this, you have mistakes. On the training set, this is all about classifying a training set. There is nothing here about generalization to new data. To study the generalization to new data, you should do the teacher-student calculation. And I will not do it because, because I have to stop in 10 minutes. So anyway, so there is this phase transition. So there is this phase transition, and you can compute it with the replica method. Yes?
What is capital N, and alpha? And capital
Yes.
N number of training examples.
So capital N is the size of the system, the size of the input, which is the size of the sigma vector. So it's like in the p-spin. Capital M is how many training examples I give you. So if you are classifying images, how many images do I give you with their label that you can use to train your machine? And alpha is the ratio of these two.
So if alpha is very small, it means I have very few training examples, so I should not be able to classify it.
No, if alpha is very small, you have very few training examples and very many parameters. So you are able to classify the training set. Now, if I show you a new point, probably you have poor performance on the new point. So the generalization, what is called the generalization error, is going to be large at small alpha, and it will.
Less than 1, probability of solving should be 1.
Yes. Not one. Not one. Let me draw alpha. This is a bit counterintuitive, but the critical alpha is actually 2. So what is the phase diagram of this problem? So you do your replica. I mean, now the problem is, the problem looks, okay, I forgot one thing. I mean, to do statistical mechanics, we would like to have a Hamiltonian. So let me introduce a Hamiltonian. I will write this as a sum over M from 1 to large M of a potential V that depends on HM, where HM is the constraint that I erased. Sorry. So my constraint is that I want HM to be positive, okay? So I want this thing to be positive, so what I will do, as I did for the coloring, for example, I have a constraint, I want the constraint to be positive, I will put what is called here a cost function or loss function or whatever you want to call it. That is a potential, and it is 0. It is 0 if my constraint is satisfied, I'm happy. If the constraint is not satisfied, I'm not happy. So I will put a penalty, and the penalty, I don't know, you can choose what you want. People have, in machine learning, people have invented many different losses. One that I like that is convenient is just to put h square here. Let's say h square over 2, but well. So when h is negative, you put a penalty h square. When h is positive, you are happy. The reason for the h square is that if you want to do gradient descent, it's smooth. I mean, it's the gradient is continuous here if you take that. But you can take other functions. So now the problem of finding a solution to the problem of describing this SAT-unsat transition is reduced to the problem I have to find the ground state of H. Let's say the ground state energy, I normalize it by n, and if the ground state energy is at 0, I am in the SAT phase. If the ground state energy is positive, I am in the unsat phase. Okay? I think I was answering to some question. I don't know. Okay. Sorry. And so now the problem becomes the problem of doing statistical mechanics of this Hamiltonian that looks a little bit like the p-spin in the sense that you have a spherical spin of n dimensions, and you have a Hamiltonian that is random because the xi are random. Okay? So you have to do, to compute the ground state, so you have to do, for example, the thermodynamics at finite temperature and send the temperature to 0. So if you do the, yes, I was answering to the question about the value of alpha critical. So what happens if you draw the phase diagram of this thing? So there are two control parameters here. There is k, the parameter that is here. There is alpha, the fraction of m divided by n. And then there is temperature, but we want to send temperature to 0. So this is the phase diagram in the plane of alpha and kappa at 0 temperature. And this can be computed, as I told you, using replicas. So for kappa positive, the calculation is the one that was, so kappa equals 0 is the cover result, and the critical value is 2. For kappa positive, the critical value depends on kappa, and it is the one computed by Garner. So here you have the SAT phase, and here you have the unsat phase. What is important is that for kappa positive, the problem is convex. I told you that you are doing intersections of spherical caps, so it's always convex. So you don't have any glass transition because the space is always one single minimum. So what happens is that, well, a simple thing you can do is to generalize the model to negative kappa. It doesn't make sense in terms of classification because, well, because kappa is a stability, so you want it to be positive, but formally you can still do it. So it's still a problem of satisfying constraints, except that I shift this value. So if kappa is negative, then the spherical cap is not anymore a cap, is the inverse. I mean, it's each point. So for example, the point xi1 excludes this part. But now if you have a second point that excludes this part, now you can have two disconnected regions of solutions. So now the problem is not convex anymore. And so you can have a glass phase. So this is a calculation that was done by Franz and Parisi first, and then we also we have another paper altogether with Franz, Parisi, Urbani, and Sevelev. So you can extend this line. So you have, here you have still the sat phase and the unsat phase. But now, around the transition, there is a glass transition here. So it's a bit complicated, and I don't want to bother you with all the details, but there is, here there is an alpha MCT, let's say, and an alpha K. So in the notation of the P-spin, here, the sorry. What did I do? It's the other way around, of course. So here the problem is sat. You have solutions, and they are all connected. You can, the system is paramagnetic. You can, it's ergodic. Here it's the dynamical glass. So here you still have solutions, but they are disconnected and they trap the dynamics. And here here is the true thermodynamic glass, where the number of states is not exponential in n. And well, at some point, these two lines merge, and this becomes a continuous transition that I didn't discuss. Anyway, the point I wanted to make, and then I stop, is that the perceptron with positive kappa is a bit special because it is convex by construction. You can solve it with replicas. You find that the thing is always replica symmetric. There is no glass phase, but it has a transition from sat to unsat. In more general problems, like, for example, coloring or multi-layer neural networks, when you add layers, people have done something in that direction. The problem generically becomes non-convex, and then you have a situation that looks like this, where when alpha is small, the problem is sat, and on top of being sat, it is easy to find solutions because the system is ergodic. So if you do gradient descent, simulated annealing, you will end up in a solution. But then there is a region here near the transition, so near this point. In the generic case, there is a transition to a glass phase where there are solutions, but it's very hard to find them. And then the system becomes unsat. So this tells you that this is about classification of random data, so nothing to learn. But it tells you that there is a capacity transition where for few data, the machine is able to fit perfectly the training set. For many data, the machine cannot fit the training set. And in between, there is this hard phase where, in principle, you can fit the training set, except that you can't do that by doing gradient descent or something like that. And something similar can be generalized to the teacher-student problem. So if you do the teacher-student calculation, what you get is something like that. For small number of data, you can fit perfectly the data, so the problem is sat from the point of view of training, but you don't generalize. Your vector sigma is not aligned to the teacher, so you don't learn anything. So if I show you new data, you are lost. And then there is, when you increase the number of data, there is a hard phase where in principle you could learn the teacher, but there are so many other solutions. So the teacher is always one solution to the problem because the teacher is the one who generated the data. So in principle, you could learn the teacher, but there are exponentially many other solutions, like in the P-spin. So you don't learn it because it's too hard. And then there is, when you keep increasing the number of data, then there is another transition where you maybe learn the teacher. So, I mean, you can play with these things depending on the problem. You get different phase diagrams, but I mean, you can make sense of some of these problems. So then there is a debate. I mean, the big debate now is, I think, the big debate is whether the structure in the data is important, because all these things are done, even in the teacher-student, you still use random data as input that then you label with the teacher. And now there is a debate on whether you can apply these results to images. And for this, you should follow the work of the group of Lenkas Deborova and Florent Chakala and Marc Mesar, Riccardo Zecchina and Bocconi. So they are working on this, and they have papers where they show, for example, that if you train a machine using random Gaussians with certain correlations, you get similar things that what you get on images. And so maybe not all the structure of the data matters, and there is a debate. But at least for random data, you can solve the problem using similar techniques than in the p-spin. I think I should stop so we can go to lunch. Thank you. And I'm happy to yes.